Hey everyone, my name is Joe. Thanks for having me here. Today we're going to talk about debugging our applications live in Kubernetes. You can see a GitHub repo noted up here, and that is kind of the source material for this presentation. This presentation is kind of information dense. There's a lot of slides that have a lot of details on them. I'd recommend instead of maybe trying to take pictures or jot things down, you can get the slides both on the KubeCon schedule as well as from this GitHub repo, and it might help you kind of keep track of sections that you are review it later to understand maybe how to do some of these techniques. Also, this repo is built around .NET Core. I'm not going to be doing a lot of .NET Core specific things or trying not to. I'll mention it some, but all these techniques we're about to look at are kind of framework agnostic. They're Linux specific, and they can be run against all kinds of runtimes and frameworks, not just .NET Core. Okay. So what are we talking about today? This presentation is primarily divided into two major parts. In the first part, we're going to talk about kind of building a toolset container, a sidecar, that we can pack full of a lot of tools that we're going to use to debug our applications. We're going to talk about some of the challenges there, some of the things that I've come across when I've been working on my toolset container for NetCore. And then the second half of the presentation, we are going to kind of demo three different techniques. We're going to look at perf for CPU profiling, LTTng for user space static trace points, and BCC for uprobes dynamic tracing. Like I said, these three techniques can be performed against all kinds of different runtimes and frameworks, so don't think this is NetCore specific. Also, we're going to do this in a way that we can do in production. The idea here is we're going to increase knowledge of our applications in the production environment, whether they're going through some negative moment, like they're not responding to requests correctly, and we're trying to figure that out, or they're performing well, and we just want to understand more about what it means to be performing at load or at scale. We can use these techniques to learn more about our application under those circumstances. So all of these are very low impact, and all of these are designed to be run at scale under load. And then finally, kind of a theme of the presentation here, I guess, is we are going to be performing this from the sidecar. So we want to do this in kind of a Kubernetes native way. We'll cheat a little bit, and we'll talk about that. But primarily, we're going to be doing this through the Kubernetes API in a Kubernetes native way. And we'll talk about why that can be a cool idea and why that works well. Before I get too far, I'd like to give credit where it's due. Sasha Goldstein and Brendan Gregg have both done a tremendous amount of work in tracing and Linux debugging techniques. Brendan Gregg in particular's blog is chock full of awesome information about these things. If you are interested in this field, I highly recommend his blog. Also, Sasha Goldstein did a lot of work on dynamic tracing for NetCore 1.0, and my work in NetCore 2.2 is kind of an extension of that to get that to work. And then there's two other really good links there. If you're kind of new to this world, those links are really good overviews of just Linux debugging systems in general. It's kind of a fractured world. There's lots of tools, there's lots of terms and technologies, and when you first get involved in it, it can be confusing about what's happening, all the different pieces. These are two kind of good overviews that touch on a lot of the major areas and ideas and what's going on. And then finally, my repo. Like I said, the slides are there, so like this slide, for instance, you're not going to obviously copy down those URLs or anything crazy. Grab the slides, and then you can look at them later to get some of these links and get some of the details that we might move past. Okay, so from a sidecar, why? Why do it this way, I guess, is a question, right? When I first began performing some of this, we had some application issues in production, and I would SSH into a node. It was kind of the naive approach here. Like I wanted to gain more information about a process that was running on my Linux instance, so I SSH'd in, and I ran perf. I pulled some tools. I was trying some of these techniques, and I did. It helped. I learned a lot about the application and what it was doing. But when I was done with this, I kind of had a mess. Like I had all these tools installed. Suddenly I had one node with different packages installed, and some garbage stuff I'd left around, like little notes or like files I'd output to. And I didn't like that. I didn't like that I was kind of taking this world where I had a bunch of consistent nodes. Everything was the exact same, and I had one node that was different. So at the end of these like kind of sessions where I was doing the debugging, I had the choice of try to clean up, stop caring and leave it alone, just leave it, or delete the node. And none of those felt good. The sidecar is a really neat technique because you can put all of your tools in this, or all of your tools in this container that you run alongside your application container. And when you delete the pod, then it all goes away and it cleans up after itself. And so you don't have this kind of concern about impacting the node and maybe what I could do or an impact I could have on other processes on the node. It doesn't require host access. So every organization is kind of different, who's allowed on a node or not. Maybe everybody is, maybe just your infrastructure people, maybe your devs are, maybe they're not. But the people who would normally be doing this kind of analysis are probably developers. And if they're not allowed on the node, then this kind of sidecar technique will open up some of these tools to your developers, give them some observability, give them some opportunity to see their applications better without having to give them SSH access directly into the node. It's also easy. We'll talk about why it's not easy in a second. But it's easy to build a toolset container that supports this, that has your debugging tools in it. And what I mean by easy here is it obeys a lot of the same rules that our application containers do. You can iterate on it, so you can build a container that just has perf and just does some CPU profiling and get that working, and you have a new way to see your application. And then a couple months later, you have some other problem going on, and perf's not helping, so maybe you learn a new technique or a new tool, and you keep iterating and building on this toolset container over time, and you can deploy it to anywhere you want. Also, like our application containers, it's immutable. It can be dropped in on dev. It can be dropped into QA. It can be dropped into prod. It can be dropped into our desktops, and it has this portability aspect to it. It has these kind of neat features that our applications do as well. Also, once you are in the container and you're kind of messing around with things, you'll often find, oh, I didn't think to bring this tool in, or I didn't have to think to bring this thing in, this script or whatever. You can write scripts on the fly. You can pull new tools, curl or apt-get them, and then again, when you delete your pod, it's all gone. You don't have to worry about the changes you made. You don't have to worry about what you may have done dynamically inside the container. Finally, I feel like this also supports development diversity. If you have a lot of teams, and these teams have different technologies, like you got your Node team, and your Python team, and your NetCore team, then each team can kind of build their own containers. Instead of trying to have a node, and that node has tools for everybody, you can instead have each team is building their own containers to debug their own applications, and they have developed their own techniques internally, and they can kind of maintain that on their own. Okay, why is this not easy? What are some of the challenges? What are some of the problems with trying this? I'd say the number one issue, the most difficult thing I ran across while I was working on this was when you install some applications like perf, they want to be installed for the kernel that you are installing them on. They are kernel-specific installs. If you apt-get perf right now, it will be a version of perf that is built for the kernel that you are running. So if you build a Docker file and you run it locally and you build a container and you apt-get perf, it's going to actually be for the kernel on the machine that you built it, and it might have problems when you try to deploy it to a node in your production cluster that has a different version. So some of the options there, we can bake our tooling in. Some of us are lucky enough, and we are lucky enough that all of our nodes are going to be the exact same kernel version. We have this kind of very homogeneous architecture to deploy to. And if you're in this world, that's fantastic. Bake everything in and make it exactly what you need for the kernels you're running, and you'll be in a good spot. Other things we can attempt to do, we can mount stuff from host, and we're going to do that a little bit. And that's kind of where we're going to cheat some, because it's kind of, by mounting resources from the host, we kind of blur the line between using host access or not. And finally, another option is pulling this after deployment. You deploy this and you try to pull in the tools then once you're on the actual machine and the kernel is known, the kernel version is known at that point. That approach is primarily how I have worked with my .NET Core container, my Sidecar with my toolset, is pulling these things after deployment. And while it is kind of flexible and has given me the ability to deploy to a lot of environments, I've gotten it working in AWS Kops with a Kops cluster on Debian, GKE Ubuntu. I've got it running locally, of course. It's been very difficult to keep that working, and it's been a lot of overhead to keep it working. My advice would be to remain on the top line. Hopefully you can just bake everything in and it'll work nicely for you. Also, Sidecar images can be very large. This kind of doesn't matter, and it kind of does. I mean, we don't want large container images, but you're also not pulling this all the time. This isn't a normal application. You're going to pull it at specialized moments, right? Like, today I want to do some profiling in production, so I'm going to do it. And you do it that one time, and a month later you do it again. So if these container images are a little large and they require a little bit more time to pull, I think it doesn't matter as much. But they can get very large, for sure. And they can't be added dynamically. They kind of can, but they kind of can't. And this is another cheat moment. In a Kubernetes native way, they cannot be added dynamically. A pod is immutable, and you can't inject a container at runtime. So these techniques are kind of more useful in situations where you have a known kind of like problem in application. It's intermittent. You can't reproduce it anywhere else. It happens in production like twice a day or 3 times a day. You don't understand it. You can't reproduce it. And you know this is happening, so you can then deploy a version of that application with your sidecar container, wait for the issue to come up, and then start doing your profiling. It doesn't really work for like responding to an incident. If an incident's in progress, you would have to deploy this container or this pod with the sidecar. Now, you can actually, using Docker, inject a container in the same process namespace as another container. So it is possible to pull this off if you break the SSH and node-specific rules. There was a group I was working with who wanted to run perf once an hour. And so they set up a cron job. Every hour, they would use a Docker command on the host to inject the sidecar. They'd run perf, generate a flame graph, offload that, and store that. And they kind of had this like regular record of how their container was doing and what the performance was. So that was pretty cool, but it was definitely breaking the Kubernetes native kind of rules. Okay. So what features are we going to use of? What like elements of the pod spec do we need to pull this off? The top guy here, share process namespace. This is the most important of all of the four. This is the field that makes any of this possible. By default, when you deploy a pod and the containers are in that pod, they are in different process namespaces, so they can't actually see the processes across container. They're still isolated from each other. They're all in the same network namespace, which is one of the kind of defining features of the pod, but they do not share the same process namespace. If you set this to true, then all processes and all containers can see each other, which is a requirement for kind of doing a lot of this analysis where like your debugging tools are going to reach over and start looking at your application, your actual application. We're also going to share mounted volumes between our sidecar and our application container. A lot of these tools want to communicate through a folder, through a directory on the machine. And so we need to mount the right hosts, or the right paths. We need to mount the right paths in an empty dir, and we need to share that between the two containers. We'll look at that. And then we're going to mount host paths, and that's kind of the cheat I was talking about. So we're going to bring in some resources from the host, and I'm going to talk about why I've chosen to do that in this case. And finally, a lot of these techniques are like asking the kernel for information about another process, and that certainly is a security concern, right? That's a root level kind of access. So for some of these, anything involving the kernel normally, we're going to have to set security context privileged to true. Okay. So next is the demo part. With it a little bit of luck, this will all work, and if it doesn't, then we'll figure it out. First, we're going to look at CPU profiling. This is a great technique for understanding like which functions your application is spending time in. This is extremely powerful if your application is behaving strangely and you don't understand it. If you were to run this technique and find that a specific function were eating up like 60% of the CPU time, it was on the stack constantly, and you didn't expect that, then that's a great place to start looking at maybe why that should be true. Perhaps you need to just optimize that function. Maybe there's something you didn't consider when you were writing it. And the way this works is perf is going to sample the stack of our other process 1,000 times a second, and it's just going to write out what happens. So this is a sampling kind of approach. When it does that, it's going to record those, and then we're going to use a tool called flame graphs. I believe Brendan Gregg wrote this, and we're going to use flame graphs to generate this pretty picture here. So we're using perf and flame graphs. Over here on the side, I have the pod spec. Hopefully that's readable, like way back there. Hey. Hopefully that's readable. If it's not, like I said, grab the slides. I knew that this is going to be a lot of detail. Share process namespace true. That's the most important one. It's going to be on all of these. We're going to also mount temp, and we'll look at that in a second. So notice I have an empty dir named temp, and I'm mounting that between my sidecar and my application container. And perf is going to use that to communicate some specific information. And then I also have my security context privilege true. Okay, so let's get lucky. This is a quick script that is going to exercise our application. This script is going to hit 2 endpoints and wait a second, so extremely low load, just 2 requests a second. One is going to hit an endpoint to calculate a Fibonacci value, and the other one is going to hit an endpoint that just echoes the string back directly. And we'll look kind of a second why I chose to do 2 different things like that. So we'll keep going on this side over here. We'll keep our process up, our exercise script. On this side, I have 3 pods. Each pod has 2 containers. One is my primary application container, and one of those is my toolset sidecar. So we're going to exec into our sidecars, we're going to run some clever scripts, and we're going to get some good information about our process. This first guy here is simple netcore. Oh, let's just do this. Yeah. So we've execed into our sidecar. I'm running bash, etc. I've just kind of scripted these out. Don't worry about the details of these. This is nothing spectacular or interesting. If you just start Googling this, this is like the 3rd hit you're going to get. So there is no secret sauce in this script right here. I'm going to run this script. It's going to use perf to, again, sample the stack of my main application. It's going to run for a couple seconds there, 5 seconds, and then it's going to generate a flame graph. Also notice I have to pass a PID. So I'm going to run PSX, and I can see that my main application is number 6. It's a PID6 .NET app sample netcore app DLL. If you did not set process namespace true and you ran this PSX command, you would not be able to see your primary process, and you would not be able to perform these techniques. Okay, so let's run this guy. And it will work. Okay, so I should have a little app, or a little guy called FlameGraph SVG here. There it is right there. So we've generated an SVG file, and it is now that flame graph. It is a record of our stack during that 5-second period. To quickly, before we look at the actual output, to look at temp, the reason we mounted temp is because perf wants to see a perf map in temp, and the perf map includes a mapping from an instruction pointer or a place in memory to an actual function name. Oh, yikes. Yeah, that went up really fast. And it's going to use this to resymbolicate our stack. So you don't want a stack with no symbols, right? That's annoying. It's just a bunch of stuff you don't understand. This is going to give nice, pretty names to every position in our stack, and it helps us understand what's going on. A lot of different frameworks have support for this. I know immediately that Node does, for instance. A lot of different application frameworks and platforms have perf map support, and you can perform this analysis with them. So I'm going to cheat a little bit and just open this flame graph SVG I already have instead of pull that one from the container. And so this is what it looks like. If you were to open this in a browser, it would actually be interactable. You can Control F and search it, and you can kind of zoom into different parts, but we're not going to get into all that. What this kind of means is this is our stack kind of smeared out over time. Here I can see this kind of column here, and this is maybe 30 or so %. So that means 30% of the time the stack was sampled, it was in this position in the stack. And it helps us understand what our application is kind of using its time to do. I do know, just because I've spent time doing this, that this column way over here on the right that goes real high is my actual HTTP pipeline, and that's where my requests are being serviced. If I were to see this thing take 99% of the whole thing and some call at the very top was a huge amount of time, I might want to investigate that call. Perhaps that call is taking way too long, and I need to understand why. Okay. Okay, static trace points. So a static trace point is a pre-instrumented point in your application that you want to later record, basically. The reason these things exist, because you think, oh, that's logging, right? I'm going to add a log line. It's a place in my application I want to record. But static trace points are frameworks that are designed for very, very high volume, things that you can write in the critical path, and you can record this information and have low to no impact on your application. If you were to log 1,000,000 times a second, you would crush your application and spend all this time logging. You don't want to do that, right? But static trace points are designed for these very high volume kind of events, these high volume logging events. It does require pre-instrumentation, though, so you have to spend some time building these into your application. We're going to use LTTng and Babel trace primarily. LTTng is a framework for collecting trace points, and specifically we're going to be doing user space trace points. So our application in user space is going to create events and pass it to our LTTng daemon in user space. This particular technique doesn't require kernel access at all, and you'll notice there's no security context privilege for this one because it's just application data in user space being passed back and forth. Babel Trace is a good tool to kind of dump the results of this, the events. And Trace Compass is a cool UI, but we won't get into that. So you can actually pull all these events and kind of see them in a nice UI on your desktop and kind of work with that with Trace Compass. So share process namespace true. It's going to be on all of them. Volume mounts, var run LTTng, because for similar reasons as temp, or mounting the temp directory for perf. Var run LTTng will be used to kind of communicate between the two. Okay, so this is the script we're going to run this time, trace static. So these are a bunch of LTTng commands. We're going to start a session. We're going to give it specific information about the application we want it to record events from, and then we're going to collect those events for a few seconds, and then we're going to shut it all down, and we're going to look at the events that came out of it. Like the other one, I need the PID. This will be 6 as well, probably. Yep, there it is. And cool. The reason we're mounting var run LTTng is because LTTng wants to communicate through a Unix socket, and by default it puts it in var run LTTng. So for this to work at all, both of the applications need access to the same folder, essentially, and so that's why we mounted this one in an empty dir. And then I can run Babel Trace and kind of just throw these events out. This is obviously not super useful, right? Like, what can I learn from just blowing those events out to the console? Not a lot. But Babel Trace does support Python extensions, so you can kind of write Python scripts to analyze this. And then also, like I said, you can use Trace Compass. So you could bring all these back to your desktop. You can use this Trace Compass utility to kind of see all kinds of interesting metrics about your events, like how many per event type occurred, like when did they occur. You can see a nice timeline and a histogram. Cool. Also, .NET Core specifically has pre-instrumentation for LTTng, which is why I'm using it. The framework itself generates LTTng events. In fact, if you look at these are not application events. These are like garbage collection, thread creation, thread destruction. If a thread waits or deadlocks, it'll show up in these events. Finally, dynamic tracing is the newest of all these techniques. Dynamic tracing is a really cool trick to have the kernel call back to you and tell you at any point when a function is called in an application. It's particularly interesting because it requires no instrumentation. So I don't have to do any work. I can take a binary that I compiled a month ago, and I can attach myself to any function in that application, know when it was called, know the parameters that were passed to it, and know that the return value from it. This is really powerful. What we're about to see is just the most basic demonstration that does exactly what I said. But if you do get BCC working and become invested in BCC or BPF, the bottom link there has all kinds of tools out of the box that are going to let you analyze network throughput, analyze disk throughput, and understand other details about your application than just when a function is called. This one is crazy, all kinds of stuff you got to do here. This is the hardest one to pull off. At the top, I'm running this script called run native. And then I'm sharing all this stuff, and that's all related to a specific requirement of uprobes, which is what BCC is using. And that specific requirement, and unfortunately this specific requirement is not met by all frameworks, is you have to have an on-disk machine code binary to pull this off. So NetCore is built to an intermediate language, like Java, like a bytecode language. And so I'm running a script to take that bytecode compilation and turn it into machine code and lay it on the disk. I'm executing that. And only that specific trick allows us to do BCC at all to this application. Okay. Also, we're mounting, this is the cheat mode here. We're mounting user source and lib modules, and that's to get Linux headers. So to compile these BPF programs, we need Linux headers. It can be difficult to pull the exact Linux headers that your kernel is compiled with into a container running on the kernel, running in Kubernetes. So I'm cheating a bit here. I'm actually mounting the Linux headers from the host itself, and that makes this just work really nicely. I'm also mounting /sys from the host because it's using ftrace, which requires /sys. And so this is by far the most complex of all of these. Sure, let's give it a shot. Cool. So the first thing we have to do here is we generate these offsets, and I'm not going to get into that because that's very specific. But what you have to know is the exact offset that your function call begins in the binary as it sits on the disk. And so that can be very difficult to learn. You'll find when you start digging into it, some frameworks nicely give this to you. If you run that core, then awesome. Go to my repo, and it tells you exactly how to calculate these values, and you can start tracing today. In this case specifically, we're going to trace that 1A50 is the offset of the Fibonacci, the function that calculates the Fibonacci values. So we're going to trace that function. Every time it's called, we're going to know the integer parameter that was passed in. Then we're going to trace the return value. So every time it's called, we're going to know the integer value that was returned on that second line. And then the final trace line is actually going to trace the function that is calculating the echo value. So calculating the echo value is literally returning the parameters passed in, but we're going to trace that function. We're going to see the string that comes out of it, if we're lucky. Okay, so that's cool. It worked. So you can see it's not responding every time. So these 3 pods are sitting behind a Kubernetes service, and the Kubernetes service will, roughly load balance between the 3. So you should see about every 33% or so of these calls are going to actually hit this pod. So on the right side, as you're seeing, the exercise script kind of ask for this Fibonacci value. When it happens to hit this pod of the 3, we are getting information about that. We are able to see the parameter that was passed, the position that was requested. So cancel that one. We're going to start the next one. This one traces the return value. So in this case, you'll actually see it match up exactly because that's the response from the HTTP endpoint. So every time you see this one, again, it's the same function being hit, but this time we're actually tracing the return value from that function dynamically. And then to be clear, there's no special instrumentation on this application. I didn't write any special code. I just attached to a random function in the application. I can do this for any function in the application. Finally, we're going to do strings, and this kind of shows off the power of BPF. So what BPF is a technology to write a subset of C that is compiled to a bytecode that is run in the kernel, so it makes it very fast, and it also makes it very fast and very performant. But it's only a subset of C. It can be kind of rough to work with sometimes. In this case, we're attaching it to a uprobe, and we are able to take the .NET Core internal string representation, which I think is UTF-16, I'm not 100% sure, and then extract that string and display it on the console. Perf also supports dynamic tracing, but it only does it, and it supports strings, but it only supports null-terminated strings. So you can't actually do this with perf, which is it shows off the flexibility of BPF. Basically, every time these functions are called, I'm running a little program that I wrote. I'm telling the kernel, please run this program every time it hits. And you can do all kinds of neat things with that. You can calculate a histogram. You can take some internal data, internal in the memory to the application, and represent it in a way that makes more sense to you outside of the application. And then, like I said, if you get into this field, or if you start doing BCC specifically, you immediately have access to just a stack of tools that exist on that repo, that BCC repo. How am I doing on time? Oh, pretty good. Cool. Okay. Yeah, thank you all for listening to me. That was cool. If you have any questions, let's do that part. That's Gotham if you know Gotham. He's really cool. He works for GitLab. And if you don't get to your questions now, please visit me at any moment at the booth. I'll be over there a lot, tomorrow afternoon specifically. You can ask me questions then too.
All right. Who wants questions? Who has questions?
Ben.
Ah, there we go.
Sorry.
Is there any way to inject these tools into an already running pod?
You can, but you have to cheat and do it from Docker on the node. So Docker has a specific command line parameter that says inject into a process namespace of an existing container. So you can do it if you let yourself break the rules and run from the node. But other than that, Kubernetes pods are immutable and you can't. Although I heard somebody say that they were kind of working on something like that. Don't swear to that. I didn't say that. Never mind.
So,
Okay, you've heard this too, so I'm not crazy. Awesome.
to follow on from that, is that thing that someone's working, is that the kubectl debug command? Or
Okay, yes. I've heard it was debugging or injecting a debug container. So once that exists, then I think you could probably do this dynamically, inject the sidecar dynamically, yes.
Will this model change with Kubernetes 1.16 with the terminal containers? So will you still use these sidecars?
What's in it? Sorry.
Sorry. Will you still use the sidecars with Kubernetes 1.16 with thermal containers?
The container is the sidecar, right?
Yes.
Okay, so
But you can, with the thermal containers, I guess you can connect these without the sidecar.
right, I think that's what those guys are talking about. I just actually heard about that yesterday, so maybe I'm behind the times on this one. I'm on 113 or 14, so yeah.
Okay, so
Thank
Yeah.
you.
maybe in a couple of weeks.
Yeah.
I actually, over here, I actually didn't have a question. I was going to clarify that, yeah, 1.16 is going to be running ephemeral containers,
Okay.
which means that you'll be able to launch additional stuff. And
Is that beta or alpha in 116?
give me 1 second. I just got the page open. It's alpha.
Okay, so if you set the feature gate flag, thank you, Josh Nord. If you set the feature gate flag, then you can have access to this, and then when it elevates to beta, it'll be general. Cool, thank you. Thanks. You could run delve in a container if you're running Go and expose the remote port. So I can't really comment on that. I've only done .NET Core and Go remote debugging, so I'm not sure. Would be my answer. Cool.
All right, thanks.
Okay, cool. Thanks, man.